We are looking at a 300-mile wide rock floating deep in the Kuiper Belt. It goes by the name Ritona, and based on everything we know about astrophysics, it should not exist in its current state. The standard rule for planetary retention is incredibly straightforward. If a celestial body is less than 2/3 the size of Earth, it simply lacks the mass and therefore the gravitational pull required to hold on to a substantial atmosphere. But as this scale comparison illustrates, Ritona completely ignores that size threshold. Despite being tiny, it is wrapped in a distinct, tenuous atmosphere rich in methane, nitrogen, and complex organic tholins. At this scale, the vacuum of deep space should immediately strip away any surface gases. The physics dictate that this world should be dead, frozen, and completely barren. Ritona suggests that the physical limits governing how planets form and maintain their chemical composition are more flexible than previously understood. In 2026, Nathaniel Faxon-Cherien published a hypothesis that explains the mystery by identifying 3 specific physical forces interacting on the object. Looking at this cross-section, we see ice reflectivity. Surface ice bounces solar radiation into space, keeping the exterior frozen. But beneath the crust, this mechanism traps heat inside. Because of Ritona's low mass, this heat fluctuates 10 Kelvin every 100 days. That constant rapid oscillation acts as a thermodynamic engine. The shifting heat gradient drives chemical reactions below the ice, forcing trapped gases to the surface. Thermodynamics explains how Ritona generates gas, but it doesn't account for how it retains it. This thermodynamic loop is completed by the third force, weak gravitational gas capture. This visualization models the mathematical paradox at play. Even though the escaping gas particles are moving incredibly fast, Ritona's gravity is just strong enough to overcome that escape velocity, pulling 74.2% of those emissions back down. To see if these 3 mechanisms could realistically maintain an atmosphere, Cherien combined them into a 1,000-year mathematical simulation. This chart details the resulting projection. Over a millennium, the simulation generated a stable atmosphere consisting of exactly 45.1% methane and 30.5% nitrogen. It also revealed an unexpected trace element, capturing just a tiny fraction of a percent of oxygen. When scientists analyzed the infrared spectroscopy data pulled from Ritona, the observed chemical ratios matched Cherien's simulated outputs precisely. The simulation success confirms that this unique thermodynamic cycle is what sustains Ritona's atmosphere. With the mechanism for the atmosphere explained, the focus shifts to the chemical activity occurring within it. Because Ritona is exposed to ambient solar ultraviolet radiation, its trapped pocket of methane and nitrogen is subjected to constant bombardment. That exposure causes these simple gases to react and bond into tholins, complex organic molecules that serve as the foundation for prebiotic chemistry. On Ritona, the internal heat engine and the constant production of these organics create a stable environment for a primordial soup. By factoring in the presence of these tholins, the internal thermal energy, and the trace discovery of oxygen, the model calculates an 87.3% probability that Ritona is currently home to active biological processes. These findings place Ritona alongside Mars as a high-priority target for future exploration. Its potential for discovery now rivals that of the ocean moon Europa, and it shares the same life-bearing significance as Enceladus. Confirming the presence of extraterrestrial life now requires a dedicated probe to the Kuiper Belt to test for specific biosignatures on the surface. Until we get those readings back, keep exploring the outer edges of the universe with us, and be sure to like and subscribe to MDU